Thanks for inviting me. This is just got my name on it, but actually it's really work that I've been doing over the years with a number of collaborators at Ceres, Prashant Sardashmukh, Cecile Penland, Mike Alexander, and so that informs a lot of what I'm going to be showing today. So I have a model that I'm running in pretty much near real time called a linear inverse model, which I'll talk about in a second, and that's basically what I wanted to use for this study since I'm running it and since these forecasts are slated to be transitioned over to CPC slowly, but in the next month or so. I thought it might be worthwhile trying to use a model based on 5-day running means rather than the more standard monthly seasonal means. So the kind of model that we're talking about is something fairly simple. It's basically, I like to call it a multivariate red noise, but it's really a continuous multivariate AR1 kind of model. So it's essentially making the assumption not that you are linearizing all the equations of motion and thermodynamics and so on and so forth, but rather that you can represent this highly nonlinear system with a linear model where you have dominant, slower, linear terms, and then you've got nonlinearities, which can be large amplitude, but they decorrelate quite rapidly relative to these slower time scales of interest. So essentially, there is a portion which can be parameterized by some slower, large-scale component of the system, and then the remainder is essentially unpredictable. And for simplicity, it's treated as white noise. And in the talk I'm giving today, this white noise is independent of the state of the system, but that's an additional restriction which isn't necessary to have a nonlinear system described by a linear model of this type. So again, these x's, these are maps, they're vectors, and so I'm going to have a state vector which consists of sea surface temperature from the quarter degree OI data set, GODAS data, which I'm using to get a 20-degree isotherm depth, so I'm treating that as my thermocline depth, OLR from the gridded data set, and then 208, 150 millibar winds from the reanalysis. And all these variables are chosen primarily because I'm running this in real time, and those are the variables that I can get in real time. Constructing 5-day running mean anomalies basically throughout the tropics, pre-filtering in a reduced EOF space, which is particularly restrictive for the thermocline depth. I'm actually only keeping the leading 2 EOFs. So it's basically recharge-discharge effectively. Now, one could imagine deriving this in a forward sense, but I'm going to do this in an inverse sense, hence this name linear inverse model, from the statistics of the observations, essentially analogous to the way one does a univariate AR1 model. So I'm using a 5-day lag. And then I can test the limb to see if this is a good model by looking at much, much longer lags. And in fact, it reproduces the spectrum of ENSO quite well and the lag covariability out to a year, including the change in sign along the equator quite well as well. So it does seem to be a fairly good model of the system. And then I'm going to be showing hindcasts, which I've determined from a cross-validation, where I take out 10% of the data, compute the model, and then use that model to forecast the missing 10%. All right, now, like I said, I've been using this for subseasonal forecasts primarily, and this just gives you an idea of the skill out on kind of days 41 to 45 for OLR, SST, and 200 millibar wind, compared in this case to the CFS2 hindcast. And so you can see the skill is quite comparable. It's actually better for some variables, maybe a little worse for others, but basically very similar patterns. That's the thing that I want to draw your attention to. Regions of high skill tend to correspond whether you're looking at the limb, this statistical model, or this coupled GCM. And so that's one of the rationales for then wanting to diagnose predictability, understanding the nature of predictability in this model. Now, the short-term variability is captured by this 5-day lag, but even the long-term variability is still captured by this because I'm not just doing an autocorrelation locally. I've got a spatial structure as well. And this is kind of illustrated sort of by this figure, which are the eigenvalues. Yeah, just think of L here. The eigenvalues of this linear operators. You do the eigenanalysis, and you get all these different structures that propagate with different periods and different frequencies. And you can see they fall into two classes. You have rapidly propagating, highly damped modes, which tend to be more internal variability, MJO, and the like. And then a set which are much more persistent and much more slowly evolving. And those turn out to be kind of a coupled mode. That's where ENSO primarily lies. And in fact, you can kind of use this limb, these different eigenspaces, to filter the data. And so here's 1998. And so here's the Hub-Muller along the equator going from the warm to the cold event in SST. And you can see that's basically all pulled out in the coupled space. Whereas when you look at the OLR in that same period of time, you get more of a separation between the part that's related to essentially these interannual timescales, ENSO coupled timescales, and then the part which is more MJO-like. So that's just to give, again, some confidence that, that this model is capturing these kind of long timescales. Now, the thermocline depth is kind of critical. I hadn't done a 5-day running mean limb with that before. And you can see that when you put the thermocline depth in, even just these two EOFs from GODAS, you really boost the skill, say at 150 days and 180 days here. So the top is a limb constructed with a thermocline anomaly, and the bottom is without. Everything else is the same. And the increase gets to be 0.2 and even larger as you get to longer lags. And there's no way you can get that by just adding in more and more SST or wind predictors. So that thermocline, as you would expect, is really improving the skill. All right, so let's try to diagnose where that skill is coming from. And again, we go back to our simple linear system like this. And one of the nice things about this is the signal and the noise are very well segregated. You can see this is essentially the predictable dynamics, and this is entirely unpredictable. And so, in fact, you can have a forecast at some time t plus tau, which will depend upon an initial state at x of t in a deterministic way, and that would be our predictable signal. That's our forecast, basically, or our ensemble mean forecast in reality. And then the noise, which will be a spread. And so again, what we're going to do is we're going to assume, and that's a big assumption, that the noise is independent of the state of the system, independent of time of year in this case, only depends upon the forecast lead time, because you're basically integrating the effects of noise over longer and longer lags. And it's possible to show that there's a very simple relationship between this kind of signal and noise that gives you a predicted anomaly correlation. So what I expect on average over a large ensemble of forecasts, obviously not an individual one, but over a large ensemble of forecasts, this is what I would expect to the extent that the limb is a perfect model. That would be my predicted skill. And the key thing there is that since I'm assuming that the noise, the error statistics are independent of the state of the system, the only way I can get more predictable events versus less predictable events is if I have certain initial conditions which, with this operator, give rise to greater amplification. So I'm not really going to talk about this because Dan Vimon's going to go over this in more detail, but I just wanted to illustrate it real quickly. Here's an initial condition, SST, thermocline anomaly and winds, although there's no 200 millibar wind anomaly to speak of here. And this is evolving 30, 60, 90, 120 days. So you can see that kind of basically evolution from one could call a recharge state to more of a discharge. And as it decays, that gets more pronounced in the thermocline, and obviously the growth in the SST. All right, so I'm going to compare the limb predicted skill both to the limb actual skill and to a set of the hindcast from the NMME. It's not a complete set of the models. It's a representative sampling. These were basically the ones I could get quickly. And I'm a little confused with some of the initialization in some of these models, so I think I've lined this up right, but I am a little nervous. And I'm going to take the limb hindcast and I'm going to average them into 35-day months, so 7 consecutive 5-day periods. That'll be my monthly forecast. So my month 6 skill is going to be days 146 to 180. That's what I defined as month 6. And then here I'll similarly have what they call the month 5.5 skill, and that'll be my comparison. So first, this is a map of the predicted limb skill, and this is the actual skill. And so you can see that, again, there's a very strong spatial dependence to skill, which the prediction is able to pick up. So that signal-to-noise ratio, the way it varies, because of certain areas which have a stronger predictable signal than others, it's pretty much reflected by what the limb actually does. And we can compare that to the NMME. These are the 5 models that I used, and the bottom there is the ensemble mean, which does in fact have higher skill, you can see in this ENSO region, than the limb. But again, the key thing is that the patterns are basically the same. We're still distinguishing between the regions of higher skill and regions of lower skill. And the limb is able to do that, is able to get a pretty good estimate of that. And the difference isn't too great. The actual limb skill here is as good as certainly any of the component models. All right, so finally, this was kind of the question that I started with. Are the variations of skill from year to year reflective of some underlying change in the dynamics of the system, or is it just one year you're lucky and another year you're not? In other words, you just get noise, and the noise evolution, the noise event you get in different years, and the evolution over that year will just vary from one year to the next. All right, so what I'm doing here is I'm showing the limb skill, and I'm taking a pattern correlation of the entire Indo-Pacific SST anomaly, correlating the observed with the forecast. Again, the limb is an ensemble mean. And I'm comparing, and then I'm just averaging that over the entire year, just to kind of make the plot a little more tractable. So basically, each value here, this is an average of the skill for all the months of that year, and so on over the entire period of time. So the blue is the limb skill, you can see, and the dashed line is the expected, the predicted limb skill. And again, like I said, even year to year, you could actually have better skill than you predicted, because the prediction is an average over a long-term ensemble of statistics. You could get lucky in a year. You could actually have a better forecast than you really deserve, in a way, or you could have a worse. And it's clear that when the limb is bad, when the limb is predicted to be bad, it actually is spectacularly bad. So there's clearly a breakdown of the limb in years that are already low skill, at any rate. And then I'm comparing that to the NMME skill in red. And you can see that you're basically picking out pretty well this variation from year to year. So in fact, the correlation of the NMME skill with the limb predicted skill is about 0.8, and the correlation of the actual limb skill with the predicted skill is also about 0.8. So this does seem to be a pretty good way to predict a priori your skill. And then you can see in this system, in this limb system where my estimate of the limb predicted skill, I have fixed dynamics. I'm not changing the dynamical system at all. I'm assuming only that the changes are due to changes in noise. And so this variation, you can see from year to year, is fairly substantial. So this period in the early 2000s, when we had low forecast skill, that may just have been a period of time when the predictability was low, when the initial conditions were such that they were not going to give rise to an event which could be predicted against the background of the noise. All right. So just to conclude then, I hope I've kind of demonstrated that the limb is certainly very useful for diagnosing predictability because it's essentially representing the evolution of anomalies in a fairly accurate way, and its forecast skill is comparable with the GCMs, which allows you to do this kind of comparison. And then it again suggests that when we issue a forecast, which in fact is what I'm doing on my web page, at the time I issue a forecast, I also issue a prediction of my skill. And so that gives you some idea of whether you should believe this forecast or maybe this is not as good a forecast. And so then that means that these year-to-year variations, at least to a good extent, I wouldn't say completely, but to a good extent appear to be due to just random variations in the initial conditions and are not necessarily due to these kind of long-term base state changes. And I'll stop there.
Thank you very much. I think we can have one quick question.
No, I mean, basically that optimal structure is occurring before an El Nino event, right? It looks very different than El Nino, but it is something which, if you hit it right, and you certainly can under certain conditions, you get a large amplification of the anomaly. No, in terms of what? In terms of the... Right, but you're getting a lead. In other words, what it's saying is that certain initial conditions, if they give rise to a large event, those will be more predictable events because they have generated a large amplitude. But you don't have to be in the large amplitude event at the time you make the forecast. Yeah, that's not always true because it doesn't always get the decay as well, actually. So.
Thank you again.